All right, and so we've been exploring how the layout of the periodic table, this one's blank, is related to something called orbital filling order, and we've been using this thing to help us out. And we know that if we have an element of, say, hydrogen, which is in the first column and in the first row, we know that there is a connection with the fact that hydrogen has one electron. It's the same as its atomic number. And that if we are going to determine what's called the electron configuration, we're looking at this guy right here, which shows all the available orbitals at the first two energy levels, and we'll get into what the third one does. And so we know that when hydrogen is filling its orbitals, it only has one electron, and we're going to put it in the 1s. And that each of these orbitals can hold 2 electrons as long as they are spinning in opposite directions. So if we go to helium, which we happen to know has 2 electrons because that's helium's atomic number, we know that the electron configuration for helium is going to look like this. We're going to put 1 electron in the 1s, and each of them can hold 2 as long as they're spinning in opposite directions. So we can put a second one in the 1s, and according to the Aufbau principle, we are filling the lowest available energy orbitals first. We should also know by now that there is a connection between the fact that helium has 2 electrons, they're filling the 1s, and there isn't any more room. So that if we were to go, for example, to, say, the next element on our list, which would be lithium, and that's right here, lithium has 3 electrons. And we should see by now that there is a connection between lithium having 3 electrons and the fact that it is located right here, second row and first column. Because lithium having 3 electrons, we're going to put 2 in the 1s, and there's no more room. So now we go to the second energy level and put them in the 2s. So there is a connection here. In fact, hopefully we'll see by the time we're done with this that every element that's in column 1 ends in electron configuration S1. And if we did one more, for example, if we were going to say, look at the electron configuration of something such as neon, which is here, notice that it is in the second row and is in the final or last column. Well, neon's got 10 electrons. And I'm going to use our faster version by indicating an electron with a slash and an electron spinning in the opposite direction with a slash in the opposite direction. So neon's electron configuration is going to look like this. We've got 10 electrons. We've put 2 in the 1s. There's no more room. So we're going to put 2 in the 2s. There's no more room. Now we're going to fill the 2p's, and we're going to observe Hund's rule by keeping them separate as long as we can. 5, 6, 7. And now that there are no more empty available orbitals, we'll share 8, 9, 10. We should see that there's a connection between the fact that neon is in the last column of the second row and that there is officially no more room in the second energy level. And so if we were going to add one more electron, say for, sodium, which is here, which has 11 electrons, the electron configuration of sodium would involve going to the third energy level. Hopefully, that's pretty evident. Well, today we're going to go beyond energy level 3p. And, of course, if you've been paying attention, you should probably have figured out that 3p is all of these guys. because every noble gas is going to end something P6, with the exception of helium, because it doesn't have enough room for P6. It doesn't have enough electrons, only S2, so it ends S2. That's okay. Everything in this column is going to end something P6. Something weird happens when you start to go beyond P6. So here is our orbital filling order chart, and we see this for the first time. Let's zoom in a bit. Now what this is showing is that the orbital filling order goes in increasing energy in this direction. And so we're going to fill 1s first, then 2s, then 2p, then 3s, and then 3p. And here's where it gets a little interesting, because if we are going in order of increasing energy, the next one after 3p is not 3d. The next one that is lowest in energy is actually 4s, and then 3d. So that might explain why we see something like this. Let's zoom out a bit. And let's try the electron configuration of something right here. This is potassium. This has 19 electrons. So we're going to fill potassium with 19 electrons, and we're going to use this filling order that is a little counterintuitive. So we've got 19 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. After 3s, we go to 3p. So here's 13, 14, 15, 16, 17, 18. And after 3p, the next place we go is not 3d, but 4s, 19. And so potassium's electron configuration would look like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That might explain why potassium is here in row 4 and in the first column, because everything that's in this column is ending S1. Now, before we go any further, you might be looking at this and thinking to yourself, man, that takes a long time to write out. I sure wish there was a shorter way, a quicker way to indicate the electron configuration of something like potassium. There actually is. If we remember that everything that is in group 18, everything that's in column 18, that's this guy right here, ends something P6, with the exception of helium, because it doesn't have enough electrons to get into the P6. That tells us there's a bit of a shortcut here, because these guys in row 18, let's remember that these are all what we call noble gases. So what we do when we want to use a little shortcut is we'll pick the noble gas that is closest to our target element without going over. We don't want to use this one because that has too many, right? Potassium's in row 4 and it's got 19 electrons, but if we were to go all the way to the end with this guy, which I believe is krypton, that's got way more electrons. We don't want to worry about that. So, I mean, it's going to have 36. We don't need to go do that. So we're going to use this one, which I believe is argon, and this is the noble gas that is closest to our target element. And if we remember, because it's in row 3, it ends 3p6. So here's the trick. We're going to use this part of our electron configuration to give ourselves a little bit of a shortcut. And so a shorter way to tell us the electron configuration of potassium would be to say that it has the exact same electron configuration as argon plus 4s1. And this is called noble gas notation. Let's try a couple more of these. You might have noticed that we've been avoiding this middle section here. And this is a section that we refer to by a couple different names. It's often referred to as transition metals, but we'll worry about that later. Right now, what we're interested in with this section is that it is going in an area we've avoided so far. In fact, we sometimes refer to this section as the D block, because this is the first part of the periodic table that starts to fill D's. And let's take a look. Let's do one like titanium. It's right here, and titanium has 22 electrons. So let's use this guy and we'll figure out what titanium's electron configuration looks like. So 22 electrons, we're going to put 1, 2 in the 1s, 3, 4 in the 2s, 5, 6, 7, 8, 9, 10 in the 2p's, 11, 12 in the 3s, 13, 14, 15, 16, 17, 18 in the 3p's, and now there's no more room, so we're going not to 3d but to 4s, 19, 20. And because 3d is slightly higher in energy, this is where the remaining 2 electrons go, and we're going to keep them separate for as long as we can. We're going to refer to these eventually as something called an unpaired electron, but we'll worry about that later. So if I was going to ask you to write out titanium's electron configuration, you would say 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. And if you didn't want to write all of that, you could say, well, it's got the same number of electrons as argon plus 4 extra. So we're simply going to say that titanium's electron configuration is the same as argon plus an additional 4 electrons that are in 4s2, 3d2. And that's it. Let's do one more, and we'll crank this up as far as we're going to go. So here is this diagram with every possible available orbital that any atom can hold. That goes all the way up to 7p. 7p is the highest. We're never going to go quite that far. Let's try one like niobium, which is right here. Niobium has 41 electrons, and we're going to use this chart to help us figure out where they go. And this filling order gets a little counterintuitive, so we're going to add one quick diagram here, because this makes things a little bit more straightforward. This shows us the filling order all the way up to 7p and beyond, but we're not going to do that. It works like this. These arrows on this angle show us the order in which all of the orbitals are filling, and all we have to do is connect one arrow to the next. So it works like this. If we want to find the filling order for all of the orbitals available for any element, it's going to go like this. 1s first, 2s, 2p 3s, 3p 4s, 3d 4p 5s, 4d, and so on. So let's try this technique with niobium, which has 41 electrons. And let's see if this chart helps us out. So we know that niobium's got 41 electrons, and so we're going to use this chart to help us out. Here we go. 1, 2, starting at the 1s, 3, 4, 2s, to the 2p, 5, 6, 7, 8, 9, 10, to the 3s, 11, 12, to the 3p, 13, 14, 15, 16, 17, 18. According to this chart, after 3p, we go to 4s. So here is 19 and 20. After the 4s, we go to the 3d. So here is 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. After the 3d, we go to 4p. 31, 32, 33, 34, 35, 36. After 4p, we go to 5s. 37, 38. And after the 5s, we go to 4d. 39, 40, 41. So, niobium's electron configuration, and this one's a long one, looks like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d3. If you didn't want to write all that out, you would simply look for the noble gas that is closest without going over. That's going to be this one, 4p6. Which one's 4p6? This guy right here, krypton. And so we could simply say that niobium's electron configuration, written in noble gas notation, is krypton 5s2, 4d3. All right, take it for a spin.